All right, so we're going to call this chapter 11. What we're going to do in this chapter is I like to use all the techniques that we have developed so far um, to analyze two examples, okay, two different examples. So consider this as some real world research problems. Chapter 11, different examples. The first problem we are going to look at is this system here. So this is certainly more complicated than all the examples that we have seen so far. There are quite a few parameters. Each one of them has different meanings. If you try to check out the actual system, you can easily identify x is the prey and y is the predator. Okay, so x is the prey, y is the predator. So there's this conversion rate from x to y. Okay, from x to y. The predator also died a natural death, denoted by minus sy here. This is the logistic growth for the prey, followed by the interaction terms between x and y. And obviously, this is kind of complicated as we have 1, 2, 3, 4, 5, 6, 7. 7 parameters, okay? 7 parameters. So one of the typical method that people start with system like this is what they call non-dimensionalized. Hopefully they can reduce the number of parameters. And this is not a technique that I mentioned in class, but it's not exactly that tricky to see. So first, I like to do the so-called non-dimensionalized. We let x to be ku. So k here obviously refers to this current capacity k. So if for the prey, if the maximum reaches k, in terms of u will reach 1. Okay, u will reach 1. So we let x to be ku. So u is the function dependent on t. We let y to be kv over a. Okay, kv over a. So here now we have two new functions, u and v. We would like to find out the equation for u and v. I will simply just plug this term into the first equation, okay? And here's what I have. K u prime. Okay, this is x prime. You just plug this in. X is ku. X is ku. Ku. Obviously, the ay here, okay, ay is identical to kv. So I put that on the top. Once again, x is ku plus v. And then I can factor out rku. Factor this out. Similarly, I differentiate on both sides of this formula here. I get an equation for v. So I basically do the same process, okay? Do the same process. And turns out this guy becomes this. CKU. Is it plus here? And you can quickly do a similar calculation, like what we did to the equation of u, you will be able to come up with this equation here. So now I realize we have an equation for a new equation for u and v. Cancel out the k here. So here I divide the top and bottom by k. K over a, this factor get cancelled out. I get an equation for v. Similarly, I divide the top and bottom by k. See? To further reduce the amount of parameters, we let b to be b over k, and d to be this factor down here. And this gives us a much simpler system, and that looks like this. Sorry, minus on here. See? All right. And we are still not very happy with the amount of parameters here. So I do something that's called the rescale the time. Okay, rescale the time. And hopefully that'll further reduce our problem. So here's what we do. We let a different time tau to be RT. So we're rescaling this time variable. So using the chain rule, du d tau equal to du dt times by d tau dt. That's the chain rule here, which is 1 over r du dt. And same story goes for dv dt. I have dv d tau also equal to 1 over r dv dt. And then I will replace this term with r du d tau. Okay, because that's du dt. That's what du dt is. That's what du dt is. So the final version that we're going to study is this. So this is still time variable. It's just rescaled, okay? You see the r disappear from both sides? And then we're going to define both sides by r and call S over r rho, okay? So this is a simpler looking simpler looking system. And this is the problem we're going to study. And this problem has one, two, three, four. Okay, four parameters. Four parameters. Comparing to the seven ones that we have in the original one. All right, so now let's focus on this system here. Equilibrium, U is 0, V is 0. And if V is 0, U can be 1, okay? U can be 1. So that's another equilibrium. This is the equilibrium with one of them might be 0. Solve the system. So here's the positive equilibrium. And I obviously need C to be greater than 1 for this guy to be positive. Plug into the first equation, you get V naught. Okay? So to make V naught to be another positive equilibrium, obviously here we're talking about practical cases, so we don't care about the case when they are negative, okay? So I need those two guys both to be positive. From this one, I need U naught to be less than 1. That gives me a further requirement on the parameter, that is D between 0 and C minus 1. Okay? So in summary, only if C greater than 1 and D is between 0 and C minus 1, that's when we have a positive equilibrium, okay? Positive equilibrium. That's given by those two formulas, okay? Given by those two formulas. So I'm not going to write that down again. So now let's study the stability of the 1, 2, 3, okay? Three equilibriums, okay? We are going to look at the Jacobi matrix. The linearized system, the matrix look like this. So here's the matrix. Partial derivative with respect to u, partial derivative with respect to v. So I'm going to write this down for you guys. You can double check it, okay? You can double check it. Please make sure, okay, you actually do the calculation yourself and verify this, okay? Verify this. And then at different equilibriums, I will just plug it in, okay? I will just plug it in to find out the behavior of those equilibrium solutions. 0, 0, 1, 0, 0, negative rho. All right, that is when u and phi are both zeros. Jacobian matrix at where the predator phi is 0 is this matrix. And then it becomes clear that 0, 0 is a saddle. 1, 0 is also a saddle. And part of the reason is because c minus 1 is greater than d. And that's something you guys can verify, okay? That's something you guys can verify. So now I will plug in u naught and phi naught into the Jacobian matrix. Notice there's nothing I can do with those terms other than plugging in u naught and phi naught in. And notice I did not take the precise formula, okay? I did not take the precise formula for u naught, which is supposed to be this, But that's something you can try to plug in, and that'll give you a more precise condition. And this one turns out to be 0, okay? Turns out to be 0. I want you to think about why that is 0. That is because this guy is always 0. This term back here is always 0. So now instead of write down the characteristic equation and state the results, we use the trace determinant formula. So the determinant, which is this product, but subtract this, okay, it's always positive. All right, this guy is always positive. And the trace is this one. If you add them up, okay, and apply the formula between u naught and phi naught, okay, I want you guys to verify this by yourself, but I did not complete this. This turns out to be identical to this. I want you guys to verify this by yourself. Because this allows me to quickly check the sign for t. The sign of t really depends on this part. So now I can talk about different cases. If this term is negative, so once again you can plug in the u naught. Okay, there's a formula for u naught, remember, that has different parameters in there. You can plug that in if you want. Then t is negative. So look up the plane which connects t and d that tells the behavior of the equilibrium. T negative, d positive. Okay, t negative, d positive. Then this positive equilibrium is a sink. Every solution nearby, okay, tends to u naught phi naught. Case number 2. T is positive. So in this case here, u naught phi naught is a source. Is a source. So in this second case here, I know this one is a source. So this is U0 and V0. So the solution will move out. Okay, the solution goes out somewhere. But where does it go? Where does it go? Now that we have those two guys are saddles. Where does this guy go? Does it approach to a limit cycle? Remember that? So now I need to take a closer look at this case number two. Okay, I need to take a closer look at this case number two. Remember, um, for U not V not to be a source, I need this condition to hold. Okay, so now I want to study the possibility of a limit cycle. Okay, possibility of a limit cycle under case two. Okay, under case two. And here's how we do this. Okay, here's how we do this. I like to construct a invariant region. Okay, I like to construct a invariant region. So here's 0, the origin, 0, 0. That's actually a saddle point. And I try to let u to be 1 here. And I try to let phi to be alpha. So this is phi and that's u. So I like to look at this region here. I want to study this region here. I do not know what alpha is. Alpha is something we like to decide. Okay, we like to decide. So this the equation for this line is phi equal to alpha times by 1 minus u. So you can quickly check that. All right, that's the equation for this straight line here. Which is identical to alpha u minus 1 plus phi equal to 0. So this term, okay, this term is always 0 along this straight line. So now to study the trajectory along this straight line, here's how I do it. Okay, I'm going to let w, which is the function of uv, a two-variable function, to be given by this. Sorry, u minus 1 and plus v. All right. Now let's take a look at this guy. This guy, once again, this guy w equal to 0. Okay, along this straight line because this is equal to 0. Okay, that's the equation for this line. Outside, okay, outside on this side, w is positive. Okay, you can easily verify this. Inside, w will be negative. That is when u is smaller than 1 and v is getting smaller. It will be negative. So to calculate the trajectory, I'm going to do dw dv. Sorry, dt. I'm going to calculate the time derivative. Let's calculate the time derivative of w. If it is negative, okay, meaning the trajectory will move inside. If this is positive, meaning w will become positive, it'll move outside. So this is obviously a chain rule here, where u and phi are both function of t. So you get alpha times by like u prime plus phi prime. Plug in the equation for u. Okay, here's the equation for u. It's u times by this term. So that's what u prime is. Here's the equation for phi. So if you look at this guy, it looks like impossible to tell whether this guy is positive or negative. Okay, it looks like impossible to tell whether this guy is positive or negative. So we will do something to this one. Okay, we'll play with the formula that we had. This is not exactly an easy homework problem. Okay, like I said, this is more like a serious research project, and that's why some of the calculations look kind of confusing. Phi, all right, because along this straight line here, phi is alpha 1 minus u. So I'm going to plug that in. Alpha 1 minus u. Alpha 1 minus u. I still can't tell the sign. And notice now I can factor things out. Okay, see this, there's a 1 minus u here, and there's another 1 minus u here. I can factor that out. Take out alpha u 1 minus u. And here's what I left behind. I factor this out. I got a 1 left behind minus alpha over u plus b. So if you take this term out, okay, that's what you get. And back there, you get something like this. Rho remember I took the u times by 1 minus u out. I took u out. That's what's left behind. Minus. This is a 1 here, but I'm going to take a u out. So make sure you verify this, okay? This is not easy calculation, but take a quick look. Take a quick look. So now if you look at this formula that we had, always positive. 1 minus u is always positive because on this side, along the straight line here, u is always less than 1. So this is also positive. Here you have something like 1 minus alpha over u plus b. Sorry, 1 minus u plus b. So I can always choose alpha big enough to make this guy negative. Okay, I can always choose alpha big enough to make this guy negative. So let me just say I can always choose an alpha, okay, to make this alpha big enough. So that this one is less or equal to 0. In fact, I can go ahead and solve for alpha. Alpha needs to satisfy this. So put it simply, if alpha is big enough, I don't need the exact number. We don't need the exact value, but when alpha is large enough, the w dt will be negative. Okay, will be negative. In other words, along this edge, okay, along this edge, the phase portrait will point toward to the inside. Okay, pose to the inside. Along those two edges, okay, you guys can go ahead and verify this. Along those two edges, this is how the direction field looks like. Keep in mind, 0, 0 is a saddle. Between 0 and 1, okay, along this edge, it goes like this. All right. So there's no place where the trajectory will leave. Okay, will leave the triangle region. So that's why we call the triangle is invariant. So this is something you need to verify. Okay. Thus, this triangle is invariant. Now going back to this triangle thing again, the one of the equilibrium, okay, u naught, v naught, okay, u naught, v naught will be inside here. Okay, you can quickly check that. Okay, this is u naught, v naught. Under case number 2, under the second case where u naught, v naught is a source, okay, is a source, then the trajectory will come out, but it cannot get outside of this one, cannot get outside of this positive invariant region. So that means it has to approach a limit cycle, and that's the result of Poincare-Bendixen theorem. Let me put this in a summary so you have a better idea with what I'm talking about. Okay, a summary of results. Case 1. For this case, now this is identical to this to this condition here, because normally the condition is in terms of the parameters that we have. If B and C and D satisfy this property, U0 V0 is a sink. Every solution tends to U0 V0. Case number 2. If this is greater than 0, U0 V0 is a source. All solutions started in the triangle that we constructed it must approach something, okay, it must have a limit set. But it cannot be the source because the source was unstable, okay, cannot be the source. Cannot be the source or the other saddle points. Hence, by Poincare-Bendixson theorem, there must be a periodic solution, okay? There must be a limit cycle. So this shows or proves the existence of a limit cycle, okay? Existence of a limit cycle. And this condition is very easy to verify. So I want you guys to take this condition and back home. And once again, this is equivalent to 1 minus 2D, C minus 1 minus B positive. I want you to try some parameters, okay? For example, you can choose B to be like 1/2. Choose a proper D and C so that this is positive. And plug this into the online plotter. And let it plot, okay? Let it plot. It'll show U0 V0 as a source. In the same time, there will be a limit cycle surrounding U0 V0. 0, 0, that's a saddle. 1, 0 is another saddle. U0 X0 will be somewhere around here. It's a source, but there should be a limit cycle surrounding this guy. Okay, I don't know the precise shape. So I want you guys to try to plug that in. This guy becomes a source. So maybe it'll go this way and approaches the limit cycle from inside. All right. So maybe on the next, before next example, I have another example coming up. Before next example, I can actually plug this in and print that out and show you what I got. Okay, show you what I got. All right, so that's it for this example. I have another example that'll take me another 30 minutes, so I'll just pause right here.